Hey Jawad, good morning.
Hey Anu, hey everyone, good morning. Mhm.
2 minutes to start. Okay, we're reaching some critical mass here. And Cash, to your point, the website for the Chiplet Summit, the programs have not been fully updated as per our requests. I think it will be done. But if you don't see your name as a speaker, please don't assume you're not a speaker. As the OCP, we've got our plan. We've shared with you the program that we put together for Tutorial H. So please just follow that plan. Yeah, I'm very sorry that we're not able to get the website updated. There's mistakes and other things that I've asked them to correct, but it's a slow process. Any questions, any doubts? Thanks for pointing it out, Cash, yesterday. Okay. That's good. So apologies for if your name doesn't show up right now. It will show up, but you're on the agenda, the OCP agenda, and we'll try our best to get that fixed. Any questions about Chiplet Summit? Maybe we push that later. We're first gonna have David and James talk about the assembly design kit. They're going to present to the next forum, John Stewie's forum, next week. So it's probably a good idea to get a dry run here. So James, all yours. And Javad, just a reminder, at about 8:20, I'm going to log off, and then I think we know who's the folks who are going to do their dry runs.
Yeah, Anu, if you could just get the roll call, then it will go on autopilot, but I'll stay.
Yeah, I'll just send a note out on the chat then.
Thanks.
Yeah, thanks. Can you hear me?
Yes.
Okay, thanks. So, David, you want to share something, or you want me to just kind of dive in on this?
Go ahead, James.
Okay, all right. Yeah, so this is the ADK, so it's part of the 3DK that we had talked about in a few weeks ago. So it's all part of the big family of the 3DK, which consists of, we talked about last time, the MDK, Material Design Kit. We have also like test based on the test design kit, like David presented that. So there's something that we talk about to work on, like on the package side. And then in the future, like the SIPIs, the CDK is the one that we already done before. So this is again as continuous. And let's look at like where this ATK has been used in the 2DK design on the architecture wise in the chip rate selection. So the ADK assembly design kit, which is important for the compatibility. And then we also use in the planning side for the physical floor planning. So yeah, so what is the ADK here? So objective here is trying to establish a standard framework for design integration and validation of complex like chiplet and systems. This is really driven by the increasing complexity of the modern semiconductor technologies, and then for the heterogeneous integration. And again, this is a part of the for the OCP here, and the joint venture with the JDAC. The key components here, including like the standardized file format design rules and the tolerance for efficient data exchange and interoperability, and support for the advanced design techniques like the AI, machine learnings. We have standard format that we a lot easier to do that, and then for scalability and also adaptation for future technologies. So the high-level structure, we have a header. So that provides general information about the technologies that has been used, like what kind of how many micron, and then the device family, and of course including the version. And then we do have like the include. It's part of the top level that will reference to the top and bottom die rules files. So all the associated files, I think like could be included in this here, such as like potentially the material design kits that could be included here, the package information could be included here. And then top level will define the global tolerances, such as like the linear, angular, and area tolerance values. And then we do have a version map that documents the rule version that has been currently used. And then finally, I think this is what is the most important one, where it's all details about the layers, geometry, the paths, the field and shear outlines that describe the actually the assembly like die related or the interposer related composition and element. We'll come to more details in the next few slides on this. So first, like the design rules definitions, we do have like the dimension rules that check for like the max min dimensions of the tile. And then we do have like the ratio rules that define the different ratios. And then we do have a pitch that is like max min pitch between the elements. And then there's a distance, which is like calculating the distance between like two tiles. So I think this is probably one of we've seen very often, like how close you have to you can put together between two element or components, and or how far you should be putting. I think typically there's like a minimum distance there, especially with the pressing machine. Somebody cannot press too close because like it when press too close, like the machine, it might blocking the machine that put like the press component on tops. And then there's an area that calculate the areas that is for requirements. Density typically that we use in the like the bumps. So there's a calculation of density. So it's interchangeable sometimes between the density and also like the distance rules potentially. Sometimes people like specify for example distance between two bump, what how far they should be or how minimum they should be. But sometimes it also can be defined between the rules, like the density, like how many pin per certain area. And this one, like the rule count is like the space count of the die element, such as like the bump, like how many like count, I think like maximum count in a certain area. So let's dive into some of these like the interposer here. So this is more interposer specific rules. So we talk about all these things kind of more like the dial, like related rules. Here is like we do have the interposer related design rules definition. We have similarly with the for the interposer we have a dimension constraint that ensure the interposer dimension align with the package specifications. And then we do have like the chip alignment. So like interposer, typically we press the chip on top, like the flip chip. So that we need to okay, I assume, hello. I assume that may be the background noise. Okay, all right. And then we do have like the layer alignments. So the appropriate align between different layers of the interposers. Other thing is like the interconnect, so specific design layout of the interconnects, like the layout, the routings and etc. So that would be like the defined in here, and then we do have like the 3D stacking, so that's kind of related between layer requirements there. So why are we doing this? So we just want to promote the openness and collaboration to share design formats and specifications. Enhance the design productivity by reduce redundancy and automate the key aspect integrations, and then to support the adoption of the cutting edge technology like the AI. And then lastly, also optimize resources and align with the like design best practice. So let's take a look at a few example here. Like one example is like the OCP demo example. We have talked about it in the past. So this is one example, like talking about the describing like the metal layer. You can see there are two layers here, and then there's like the thickness, the dielectric thickness, um, and then there's like the minimum right wire, and then you have like the wear size. So this is also have contain the bump size, die to die spacing, etc. Including the micro bump and C4 bump. So all these things like when transferred into using the schema that we are building here for the ATK in the XML format. So you can see on the right hand side that it's kind of snapshot of partial, I think like the information like meta thickness, and then the general thickness, that, and then dielectric thickness can be formatting into this standard format. So it's a very long file, so it will be part of the document. So we're going to show a snapshot here. The next example is very interesting that we have it from the HRL reps, which one of the government agency. They have very custom assembly rules here. They was interested in the standard that we're building, so they contribute like share with the share with us their some of the rules and assembly rules requirement there. So we took that and then we trying to fit into our schema, XML schema, and then we were able to present into this XML file format. So as you can see on the left side, they have like kind of like the antenna page, like different layers. So they have a interface trough, which is like consists of microbump. Let me zoom in a little bit. And then there are different layers like 3 to 5, they're more substrates thickness, and then there's the interface 26 NRAs of the micro pumps again. And then there's the RDL that they require the thickness information, the where the pump size density will be required here. And then they will continue to have an interface 34, 35, and then lastly there's a chiplet layer, which consists of the thickness, the bond pack, micro pump size, and etc. Again, right hand side is a snapshot that we can fit that using the schema. So and that is one of the objective here. We're trying to be enable this schema so that it can be fit all different kind of like use case on the assembly. And then lastly, not the least, is the white die example. This example is coming from the Intel originally. So just to mention, a lot of the rules here are adopting a lot of the requirement or the spec coming from the Intel. So this white die is one example that shared by the Intel. So it's really focusing on the dial. And you can see the die dimension, there's like the format of the versioning. They have the date, they have the name, the mass version, the packaging. So the header, as mentioned earlier on the version area, we can have a subfield that we can extending for all this information. So that can include like the owner's email, etc. You can get into way in details. And then another example is like the dial edge. So we have like the active edge geometry here, like different kind of like shape, like the polygon, and then you have this kind of number, like following that describing the dimensions of that polygon, and then you have like ceiling to frame, subscribe line, random scribe, active area, stepping area. They all these kind of, if you look into right hand side, like the diagonal, so you can formatting into this schema. So highlight the active edge geometry, and then you can describe polygon um, in under this polygon attributes, and then all the cell ring related attribute we can describe right these parameters, and then all the remain active area, stepping, physical. So all these things can be fit into a schema that we're defining. So that is like the main objective here again, like put into this kind of like less structure way into actual structure way, make it machine readable and can be consumed by the AI tools or agent that can use to automate a lot of the information here. So that would be the last example that I have here. And the last slide I have is the paper here. So which is the we have a draft version, and David has been help put this together, right? Submitting for OCP for review, right? Please feel free to take a look. And then we do have like the GitHub link folder where we can put all the spec and an example here. And then lastly, also the schema, which is also be attached as part of the documentations. We do again the regular CDX meetings for the 2DK is at the 8 a.m. My bad here on every other Thursday. So we alternate between ADK and the MDK. So that's all for the presentation. Any questions?
One question, James. When are we presenting this to the server committee?
David, you might have more information on this.
Yes, thank you for the question, Jawad. So we are scheduled to present on the 22nd. I'm not sure if that's Wednesday or Thursday morning to the server committee.
Okay, great. Thank you.
Yeah, thanks, David. anyone have any other questions?
Well, sounds like everybody liked it. We have a full packed agenda today for, I think, 4 or 5 folks to practice their talks, and we are definitely going to run over into the business work stream time. Raghu, I hope that is okay with you.
Hey, Jawad. Hey, that's fine. I have canceled the meeting because we don't have any topics today.
Okay,
So,
I
yeah.
also made you a co-host because Anu had to drop. So I think
Yes.
we can just go through the sequence. So it will be Cash, Rajesh, Patricia, and then Steve Halvey.
Perfect.
Okay.
Yeah, I will hang on.
If
So
I may just
Cash, go ahead.
get a word in.
Thank you,
Thanks, Jawad. Would it be okay if I just make one comment?
Please do.
Yeah, thanks. So James and everyone, actually, I just want to reiterate to everyone that OCP Academy is opening its doors very shortly. And any project like this, which is producing a white paper, would love to see a follow-on contribution, which will become an official contribution to the OCP, to create a training course that can be put at OCP Academy, and then we can market that to have people come and get trained on how to use the ADK and all the other good works that are being done in this group and other groups. So just wanted to mention that.
Thanks, Cliff. We probably should have like maybe 5-minute more discussion next time. Right now, let's just go over to Cash. All yours.
Okay. Do you see my screen?
Yes.
Okay, good.
Yes.
So I'm going to talk about the Bow Flexi, which is part of the Bow 2.1 effort. And the people involved are obviously myself, Elad, Anu, Marek, and Kevin. And we want to introduce the concept of Bow Flexi to a wider audience. And the idea behind the flexible interconnect is there are still some limitations on the standards, right? And one of the key things that I think we don't message is some of the advantages of Bow. And just to clarify, Bow supports any pitch already, okay? So unlike UCIe, which defines the widths and the heights and so on. And so the negative with the UCI solution is they have 3 different standards, right? They have a standard packaging standard, advanced packaging, and now a UCI 3D, okay? And so I think this is something that already exists with Bow to be able to support sort of any width and so on. The basic premise of what we're trying to do with the flexible interconnect is to become even more flexible, right? So you can have any number of pads and wires that you want. They can be bidirectional. You can have asymmetric data. So you can have more TX than RX, which is important for things like ADCs or memories or whatever, right? We're going to be specifically supporting single data rate. We don't fix the channel reach, so you can support a 3D type link, which is very, very short, or you can go for something else that's beyond that, right? So the idea is to enable a framework where people can make changes and optimize for their particular application. Okay, so that's the basic premise of Bow Flexi. And currently, a lot of people end up having to do custom interfaces, so they have to start from scratch. So I think that allowing Bow to support this actually makes a lot of sense. And the key thing is that both Bow and UCI work well when you're talking to the outside world or interfacing to a chiplet that connects the outside world, but they're really not optimized for power and latency when you're splitting a die, right? So a lot of people that are splitting die and want to interconnect locally run into issues. So UCI 3D does fix that, and Bow Flex will Flexi will also allow you to do things like that. I won't get into the specifics, but we do allow you to do scaling of your bump maps. You can do as few as 2. And in this particular case, it's a 2 and 2, and then you have, 1 clock, and you have a receive clock, and so as you can see, this is a very compact implementation. You can go asymmetric, so you've got TXs, actually TX is here and RX is here, and they all connect in the middle, by connecting to the clocks. So I'm rushing through this because this is already something that we have explained, and we're going to talk a little bit more about some future stuff. So I'm going through this fairly quickly. So one of the comments, certainly I've heard it, that Bow has no future. As somebody that's developing something with Bow and a big fan of it, I do want to say that there are certain future applications that are of interest. And here we're actually specifically getting into the details of what your chip is doing with our implementation of Bow Flexi. So just as a little recap, I use UCIe as an example, right? The spec is very fixed, and it says that for 16 lanes, for example, you use standard packaging. If you want to do 64 with advanced packaging, that's okay. But if you want to do 16 lanes with advanced packaging, you cannot, right? So it's very, very strict. And in our particular case, we show using an advanced packaging approach, and with 16 lanes, if we do that, we are 10 times smaller. I mean, it's just a math. If you go 40 micron pitch versus 130, you are basically roughly 10 times smaller, right? And with Bow Flexi, if we implement, let's say, a 4-lane version, we are 40 times smaller. So it may not matter to people who are building very, very large die, but in the IoT space, if you're familiar with that, 1.6 millimeters may be the size of your entire IoT device, right? So it doesn't work, right? So the key innovation is, from our standpoint, is to use a more advanced pitch, right? For even doing 130 microns. So the way we do that, we're exposing this now, is that we build the advanced PHY, and then we RDL out into the core area. So this way, the standard way of doing it, the core is limited. So imagine if you have 2 of these, and you basically have no core left. In our particular case, we route, the PHY is very tiny, and we route it over the active logic area. So this is really going to be enabled also with Bow Flexi, because we intend to introduce a 3D version, so that with a particular version of our PHY, we can also support 3D. And what this means is, if somebody's building a chiplet that they want to resell, I mean, think about it, right? You would need to, with the current way of UCIe, you have to have a standard and an advanced or a 3D. They're completely incompatible with each other, right? So, and there's a lot of interest in people wanting to build chiplets for resale, right? Which is the whole concept of the open chiplet economy, where they want to have flexibility on packaging. We've seen a lot of innovation now on packaging. So, and the bump pitches are all over the place. So it's very, very, actually, I think Bow was maybe ahead of its time with that approach. And we think it's a good solution to have a very, very flexible solution. And the other thing that everybody is sort of, I think they've woken up to because of this NAMPM thing, NOFO. But 3D allows you a lot more flexibility. It allows you to have very, very short channels, which means the latency goes way down, the power consumption goes way down. You work synchronously, so it's very similar in reality to our proposed Bow Flexi. And so we see Bow Flexi and 3D as being sort of complementary, rather than, I think that Anu had used the word completely orthogonal. So, and my wish is that as we develop Bow Flexi, that we actually make it as close as possible to UCI 3D, right? so that we could even interop with that. But that's a future thing. This is something that we're still working on in terms of the PHY design within the Bow group. So as a call to action, Bow is obviously licensed, is fully openly licensed and available, and people can join and work on that. So very quickly, that was my I'm sharing basically the future of Bow within the Bow Flexi structure. So any questions?
Cash, I have a quick question. This is Salam Abdelnader from Intel. I mean, flexible, yes. Optimized, can you do a comment about, is this the most optimized solution? From a PPE perspective.
Yeah. Optimize means different things, right? If I'm in the real commercial world, right, I want to have an interconnect that doesn't cost me anything, right? So the area cost is important. And as you know, both UCI and bunch of wires are point to point. So I just showed the area of 1 PHY at standard packaging. In reality, you need 2. Let's say you're building a system, so that's 3 millimeters square, right? So yes, Bow Flexi is optimized from that standpoint. It's also optimized from a latency standpoint. There are a lot of applications where you do not want it to be clocked, right? Because or serialized, I guess you have to be clocked at least. So running at the core clock is very attractive because you want to keep things more synchronous. Okay, but again, it's not optimized. The IoT area or I would say the older node area is not optimized for total bandwidth, which is what the HPC guys are chasing, right? And I would say that both UCI and bunch of wires, where they're pushing the data rate up, right, to now 64 gigabits per second, they're definitely optimizing for that market segment, right? But there's another world where area matters, the latency matters, the flexibility matters in terms of packaging. So it's definitely not one size fits all. I definitely want to make that statement.
Thank you.
Okay, next. I don't remember who's next in line.
Okay, Rajesh.
Jawad, is it me or Steve Helvey? I think according to Anu's list, it is Steve and then Patricia. But if you want me to go, ask me.
Steve, are you here? I don't see Steve on.
We did a quick dry run with Steve's content, Jawad, last time. And Steve, I didn't think made it last time, but Steve and I are like doing the tag teaming.
Okay.
So basically what Steve is doing is going to, most importantly, I would say, talking about the open chiplet compute marketplace. And he's going to talk about the people who are joined and the some of the stats of the visits to the website and the experience center. And I bet he'll have few. And he also has going to announce a new page that is separated out. So Chiplets has been separated out into a separate tab. So I think he'll also mention that. So I think it should be straightforward. I mean, if it's not available now, we can move forward.
Yes. Okay, Rajesh. So it's all yours.
Oh, okay, no problem. Let me share. Can you guys see my screen?
Yes.
It takes time. Actually, these are the same slides we presented in our global summit in San Jose in October. We just wanted to put it in the new format. Actually, I will skip the, and these are the contributors of the white paper, which was actually at that time it was not published, but right now it is already available on the OCP contribution list. So quickly, I will just focus on the key points we are going to talk about. So basically, this is summarizing all our white paper, which is actually very big, almost 30 pages. So focus is on what's going to be a different perspective on bringing the test component in the system in package test. Okay, so earlier it was a lag-to-draw interface test, but we expanded the scope to, and the current title of the white paper and the tutorial is efficient testing of system in package. So we are going to take a bigger approach, not just chiplet test, but chiplet in entire known good stack. So as we know, right, we are building and packaging a solution as pointed out earlier in earlier dry run, right? People were really selling the entire chiplets as a separate component. Then if we are going to integrate in a system, in a package, we make sure that the known good package is that's what is coming out. So any good one die failure, it may be functional or structural, is going to cause a problem for whole package to fail. So what we are proposing here is we need to do entire hierarchical approach so that we have to focus on the DFT strategies, design for test strategies for not just chiplet level, but also when the chiplets get assembled into a package, the post-assembly level testing is also possible for structural defect, especially when you're building using advanced packaging techniques. And that's why the standards are very important for making sure you go all the way from lowest level to the highest level of hierarchy. And functional testing is another focus of this white paper, which has also come from co-author of the paper from Synopsys. So here is one quick example why it is important. When you are building all these different chiplets of different process technologies on one packaging solution, there will be we need to guarantee that all portions shown in this top picture are tested and known. They are known to be working fine. But in addition to that, the TSVs, these two silicon vias, are also very prone to structural defects when the assembly is done. So especially these days, the system in package are coming with especially popular for HBM memories. So we have a challenge of going all the way for 5, 6, 7 stacks. And if you are having another kind of package with analog also integrated, then we have to make access to the analog portions also. So what is the current state? Current state is we have some current solutions which are actually being used. We do have when you are building a 2.5D package and you have multiple dies, it's the limitation of the access from the bottom of the package and all PCB is going to be difficult. So the proposal is we have to add functional DFT hooks inside the interposer itself, and that's a very challenging task because interposer needs to be guaranteed to be working to make the regular connections, but at the same time, you have to add these IP shown here, so you can have a control access to exercise CPU or GPU or SRAM related tests. And in addition, the major limitation of scan running at slower speed, and the expectation is we need to increase the accessibility and speed of the access of the chiplets. Is the number of chiplets on the package going high. So we need to address the reduction of the test time, which is actually covered in the later part of this white paper. So we need to we have used the protocol which are currently high-speed protocol like PCI and USB. They can be also using for the test packets sending to and fro using that protocol. So now going back to the major fundamental focus of this paper is how are you going to make the intra-die successful? Then how are you going to make this interconnection between top and bottom dies when you are going three-dimensional successful, and then entire package need to be tested. So these are the three vertical pillars which are basically highlighted in the paper. And this is nothing but a very architected use of all the standards. In addition, using the 1149.1, which is one of the most popular being used for last 25 years. But then the latest standard which is released is IEEE 1838, which gives a very, very detailed hooks to make the vertical interconnections interconnectors as well as vertical dies which are not closer to the bottom to enable their structural tests such as built-in self-tests or scans. Now here is one example is we have current in advancements from EDF folks, and this is an example of SSN. SSN stands for Streaming Scan Network, which is nothing but a very high-speed access to all the internal chiplets, which is nothing but the idea of in extending the core-based big SoCs to the idea of integrating chiplets on a package. So what is this doing is allowing the high-speed bus to go because of the limitation of number of pins which are traditionally used to enable scan test, right? It is not possible with this many chiplets getting integrated on a package. So we do access this kind of internal resources using a high-speed streaming scan network bus. So it is nothing but like a token ring protocol. And internally, the test data gets expanded, applied using compression, decompression. It is absolutely required at this design nodes that you cannot do without compression. Means is one of the methodology of expanding the complete test patterns inside the chip because of the it reduces the scan chain lengths and eventually reduces the test time. So this is actually showing one example how we can test an interconnect through interposer using a typical interconnect test algorithm, which is very traditional use of walking zeros or walking ones. So this can be also extended using this three-dimensional method. And this has been proved, and companies like AMD, Intel have actually demonstrated this into their product so that the data can be sent up using the supported flexible parallel test, which is parallel tap, which is nothing but the extension of test access port from 11.14.1 standard, but in a parallel fashion in the vertical directions. So these are the two options supported in 1838 standard, and this is actually quite standard now. Now from here, my co-author is going to talk, but she is not on call, but I'll cover just to sake of practice. So what we are talking about is when we are building a system in a package, we cannot be getting rid of functional test altogether. That's one of the important takeaway for this tutorial is functional tests are exercising some use case scenarios which are absolutely not covered by structural. The structural tests, for example, for built-in self-tests or scan tests, they do not know anything about function. And finally, when you are selling a system in a package, you better be guaranteed that 99% or 100% function is working when you are selling the chip. So a lot of requirements come from reproducing the use case. So this is what this is all talking about. And for example, in UCI and Synopsys, this actually slides as a logo from Synopsys, which Aparna is going to put there. Building on this SLM test, like a silicon life cycle management allows them to repair some of the links which are shown here in this picture. They can automatically find the spot in the link which is going between the two chips, and that's why when the die-to-die interface guaranteeing that it is working at rated speed and bit functionalities come into picture, especially in advanced packages like 2.5D and 3D. So this repair solution is possible, and you can always bypass just like repairing the memory column or row. And one is this end of this big white paper. The two important aspects are discussed very extensively is cost modeling and the comparison of different packages, what different packages contribute to the cost of the test. Because cost of the test is a major factor. So he's one of the example which I already visited, that SSN is already reducing the test of cost, because this bus can run at 300 megahertz, and this was not earlier possible because it's dedicated bus, as well as you can close all the timings between the blocks A and block B. They're homogeneous, and if you have different frequency running for block A and block B, there's a built-in mechanism to multiply and divide the frequency. So this allows us to run this bus at 300 megahertz, which is much more faster than regular scan shift frequency. And this is all accessible from IJTech. So what IJTech is doing is embedded test mechanism to allow the pattern regeneration. So this is also saving you the cost. You do not have to regenerate all the patterns for block A or block B shown in this entire big chip or SoC at the top level. You just need to, these patterns are generated at the block level and reused effectively. And that's value that is brought from the standardization. And here is another example why finally to make this entire chiplet-based system in a package economically viable, what are the limiting factors? As you can see, right, all these chiplets are going to go through the typical monolithic device test flow, and so it's not a linear curve, it's going to be exponential. So it does balance out when you're talking about reusing the already known process technologies chiplets. So that is actually added and discussed in paper. So we are closing with this comparison, which is nothing but giving components of the cost in this. And then lastly, we are going to talk about the importance of interoperability, because all these standards, which I actually went into details of describing 1687, 1838, the focus is we have to mandate that these, just like 20 years, for the last 20 years, 1149.1 board level testability was mandated by all the board manufacturers, chiplet manufacturers, and system integrators. We have to come together to mandate that we do use these standards. And especially, I would like to leave with the audience with this, that 1687 is becoming so important, especially in the coming photonics chips. Analog is going to be everywhere, and you will not be able to access the analog test, which take normally very long time compared to regular digital logic test time. You have to get this kind of interface access through 1687. So finally, we are going to leave you with that DFT strategies and effective and known use of all the standards which are basically coming from the bodies like IEEE, and there are also bodies like JEDEC that needs to be integrated right from the design phase. And we have also started the test Workstream, which Mike and myself are leading, and we have at least a very good participation. So you are welcome to join our Wednesday 8. It's a bi-weekly meeting, but feel free to come and contribute. So this is our last line. I'm done, Java. Any questions?
Okay, great. So I think that was right on time. So we move on to next one. Is Patricia online? I don't see her. Okay. The last one then, David and James, and this is your practice talk for next week. No. Looks like David dropped off. So James, you want to practice your talk for next week, or?
I think I'm good that we just had the one that the week before last week. So, and then I
Okay.
had the one earlier today. So they're all the same content. Yeah.
Okay.
Sure. Thanks.
Okay. So I think, is there anybody else who is presenting next week and wants to practice their talk here? Okay, so Raghu, looks like we'll just finish it now. So
Sounds
seems
good.
that's all good. And
Hey, Jawad, before we close the call, just a reminder that the call for papers for OCP EMEA Summit is still open till February 10th. And it'd be great for people to be thinking about submitting something around chiplets.
Cliff, what are the exact dates of that event?
29th and 30th of April.
Okay. And this will be in Dublin?
That's correct. It'll be in Dublin, and the call for papers was sent out to everyone. So hopefully somehow you've seen it. There will be a few more going around. And if you go to the OCP website and you look for the coming events, you'll also find the details there.
Okay. And do you plan to do something special for chiplets there? Or?
It depends upon how many proposals we get for speaking. If there's enough, we could have a half-day session on chiplets.
Okay. Thanks for the announcement. Anything else? Anyone wants to say anything? Okay, if not, then get a few minutes back, and thank you so much for coming to the call today.
Bye. Have a good day.
Thank you.
All right.
Bye.